Stanford University.
All right, let's get started. It's lecture 10, lecture 10, CS193P. I've been working off last year's slides, and it was different. Today we're going to talk about performance. So, you have a small little device, and you want to make sure that your apps run at full speed and with maximum use of the resources, so we're going to get into that. But first, some announcements. First things first, Presence 2 is due tomorrow at midnight, 11:59, so don't forget, get it in. Presence 3 is due the following Tuesday, and that's going to go up on the web probably tomorrow. So take a look for that, and I'll show you a little demo at the end of the class. And the most important thing here is on Monday of next week, we need to have your project proposals. So whatever you're proposing for your final assignment, we'd like you to have that in by Monday to let us know what you would like to do. On the website already, we've posted the guidelines and what we're marking based on, so please go check that out. Hopefully you have ideas. Hopefully you're narrowing them down. Get them in. So today's topics, we're going to start with talking about memory usage, talk about some techniques for reducing your memory usage. Very important on a small device like the iPhone, and we'll learn about why. We'll talk about concurrency, so how to get different chunks of your code running at the same time, primarily to prevent blocking. So to make sure that your app is still completely usable and interactable while you do stuff in the background. And then we'll just get into a few little tips and tricks at the end to help you tune your performance. So the first thing about the iPhone that you need to remember is that it's a computer, but it's a computer that's about as powerful as they were, 8-10 years ago. We're talking about very little amount of memory, slower processor. The iPhone is 128 megabytes, not the 2 or 4 gigabytes that you have today on your desktops and laptops. We have a network. Obviously, the iPhone has a network connection, but you don't know what the quality of that connection is going to be. Your user might be in the middle of a field. They might be right next to a Wi-Fi. So you need to design for both. And of course, the processor is a lot slower, so we need to consider those things as well. So performance really is a key part about making successful applications. So build your code with this in mind, and we're going to talk about that as we go. And use some of the tools that are built into the dev kit to allow you to do this. There's a set of tools called instruments that comes with Xcode, that comes with the SDK. That's fantastic for memory and performance analysis, and I'll show you some of that today. So first topic is memory usage. Some things about memory on the iPhone is that, again, we have only 128 megabytes, so we have to take a look at a few different techniques here. The first is, how do you load your memory lazily? So how do you defer using up chunks of memory when you don't need them or until you need them? Don't leak. If you know, a leak is losing a reference to a pointer in memory and basically building up your heap. So your heap keeps growing. So we're going to show you how to detect that. Watch your auto-release footprint. So auto-release is a great tool, but could cause little spikes of memory usage in your app. And reuse memory. So we'll talk about that as well. And there's system memory warning. So the OS provides a way to let you know when you're running out of memory. And you should use those opportunities to dump whatever you can. And we'll get into that as well. So first off, loading lazily. This is a common design pattern in Cocoa. The idea being that you don't actually load a resource until you need it. Now, consider you have a project that's some hierarchy with a few different view controllers, and as you tap on things, you go into different things. If you were to load all of this at application launch time, your application, first of all, would take a long time to load as you load all the images you need, as you build up all the nibs that you need. So it would take a long time. And second of all, you'd build up this big chunk of memory for stuff that you may never actually use. The user may launch an application and never click on the paths that would lead them to load these resources if you were to just defer. So loading lazily is a nice way to prevent that memory usage from happening. A few things to think about is you can also break up your nibs. So this is, again, the same sort of thing where when you load a nib into memory, you actually load the entire thing. So it unarchives the entire thing and it builds the views. If you separate your nibs into more functional areas that apply to pieces that may come and go at different times, then you can help hold back loading things that you don't need. So here's an example. In your init method, if you have some image that, let's say you have an image that responds, that gets presented to the user when the user clicks a button. One way to do this would be in your init call to actually go and load the image there. What that does is it pulls it into memory. This may be at launch time, and it may not even be needed. So another way to rewrite this is to actually do this in your getter. So if you have an instance variable on your view controller, on your class called myImage, and that has not been loaded yet, you do this in your getter. You check to see if it's nil. If it's nil, it's never been loaded. So then you go and you read it at that time. And you can see the advantage of this is that only when you need it does it show up. Good for memory and launch time. And one thing to note is that sometimes, this is a great generalization about how you should be loading memory, but you may need to consider it for your own uses. What if you need that? If you need that image, immediately to be there, then maybe init time is the right thing. If you always need that image, maybe init time is the right thing. But consider this as an alternative. And this is not thread safe. So if two different threads try to access my image at the same time, they're both going to load from disk. The first one's going to go and say, my image is nil, and it's going to go and load. And the second one's going to come in on a different thread and say, hey, my image is still nil, and it's going to load. And then the first one's going to finish loading. And then now you've got two instances of memory, and now you've loaded more memory than you needed to. So keep that in mind. And we'll talk about concurrency in a little bit as well. But the next thing I want to talk about is leaks. So leaks are probably the most common memory management issue you're going to deal with as you're writing your programs. A leak is, again, you allocate some object, and then you lose the reference to the object, and that block of memory stays in your heap. And nobody's referencing it, so there's no way to get rid of it later. There's some really great tools to find them. We'll show you these. They're easy to find, and a few little tips to help find them before even having to run the tools is to look at the naming conventions of the methods. You should, if you're using the Cocoa frameworks, you should be familiar with alloc, copy, and new. When a function is when a method is prefixed with alloc, copy, or new, you can bet that method is going to return an allocated, non-auto-released version of an object. So follow that same convention when you're naming your methods. If you're returning an object that's not auto-released, prefix it like this. And then, of course, as you use these, make sure you balance that in place with release or auto-release calls to make sure that your retain count doesn't grow. Another consideration with this is if you return from a method early, let's take you've got a big function and you allocate something at the top and you release the memory down at the bottom. Keep in mind that if you want to return early from that function, you may skip over that block that does the release. So build your methods to keep that in mind. Personally, I like to not return early unless it's the first thing you do in a function. So if you have to return early, the way I would do it is, the way I personally do it is I would use right at the top of the function as you enter, if you want to make sure that the arguments are valid or that some condition outside is already met, you check that before you do anything, return right away, and then everything else I build tends to be in if statements, and then I follow through down at the bottom with memory release. So how to actually detect leaks? Let's take a look at that. In Xcode, there's in the Run menu, there's Start with Performance tool. And you'll notice there's several different tools here. Activity Monitor, CPU Sampler, Leaks. There's a few others that are only available on the device. This is what you see with the simulator. Leaks is the one that we care about here. Each leak comes with a backtrace of where the object was allocated. So this makes it really easy. When you see a leak that's occurred in your application, it points you right to where that object came from. And you can usually balance it right there from inspection. So sometimes there are leaks in the Foundation and UI Kit classes, but it's very rare. I have found them, and you may find them too. If you do, write up a bug. But the first place to look is your own code. There's so many people pounding on these frameworks that most of these leaks have been caught before, but they do exist. So if you see anything, write up a bug. It'll probably show up on Evan's desk, and he'll fix it. But take a look at your code first and make sure that it's not yours.
Chime in real quick.
Yeah.
If I'm on. So, I mean, really here, I mean, a lot of times you'll have a leak and you'll run instruments and you'll see the backtrace and you'll see that this object was allocated in some system code that you're not controlling. And a lot of people's initial response is, hey, you know, UIKit has a leak. It's not my fault. But try to resist that urge. Maybe it's something that UIKit is returning to you that you're supposed to release, or maybe it's something that you over-retained and then forgot to release. So, yes, there are leaks in system code, but don't jump to that as your first outlet.
Yeah. Examine everything. Last line of defense, but it's useful. So this is leaks. This is instruments. This is leaks inside of instruments. For those of you that are familiar with audio, you can notice there's a little timeline here, which is actually the timeline of your application from when it started running to when you paused. And in this case, about, I don't know, just a couple of seconds in, there's a spike that shows up. And that spike is proportional to the amount of memory that was leaked. If we were to let this run a long time and you had a lot of leaks in your application, you would see this little EKG-style spikes that are of different heights. But here we have one leak, and it's in the detail view here. You see that it's 32 bytes. And it gives you an outline. And the outline actually tells you, if we step down, here's our main thread. So this is where our application got launched. We have a did finish launching. And now we're building the view. And in this case, we leaked something and view will appear. So let's take a look. Let's go actually give that a try. So I'm going to open up our leak table view. And let's give this a run. So just run it to see what it is. All right, just a little table view with some names. Last year's TAs and teachers. So it looks fine, right? Doesn't look like there's any problem. If we were actually to give this a try in leaks, I say run with performance tool. Start with performance tool, leaks. When you do this, make sure you've built your code already, because leaks doesn't rebuild. So it'll run the tool on whatever you last had. Let's skip that. All right, so we're up and running. When I click on this leaks, you see there's two different things here. There's object alloc and there's leaks. Oh, go away. We see that leaks reported a little spike. So that happened about, what is that, a half a minute, no, 0.3 minutes in, and it's 32 bytes. And here it is in the detail view. I'm going to pause. So that actually stops the application. If I go back here, it's paused. And then in my detail view, there's this 32-byte string. If you look down at the bottom here, there's a couple different views you have. One of them is the outline view. I'm going to go ahead and click on that. And what we see now is the backtrace for the item in the leak view that I had selected. And we can actually step through, and this is a little tree. So I go all the way down to the bottom, and you'll notice that there's a list of, under the library column, there's a list of the frameworks or application that it came from. The blue one is yours. So my table view, this is it. And we leaked in view will appear. So let's go to the code and take a look. Go into the code. I'm already at view will appear, but here's our function. We allocate the data right at the top. In our dealloc, we properly deallocate that data. In our view will appear, well, what do we do wrong? First, we created an array. Right? And this array, if you remember, this doesn't we're not calling alloc and init, so by convention, this is auto-released for us. But then we immediately allocate a string. Okay, we allocate in it a string. And then we add that object to the array. So we allocate a string. That creates a string with a retain count of 1. We add it to the array. That bumps it up to 2. It has a retain count of 2. When the array gets auto-released, that takes it back down to 1, but we're never going to get to 0. That string we never released. So let's do that. I'm going to say string release. And now if you see, so we auto-release an array. We create a string with a ref count of 1, add it to the array. Now we have a ref count of 2. We release, we're back down to 1, and when the array gets released, we're going to be back to 0. So let me build that. And let's run it in leaks. I'm going to start it back up. I think. Let's close this. All right, start with performance tool leaks. And here it goes. This is not going to be a very exciting thing to watch because we're not going to have any leaks if we did it right, and we should be fine. So let's actually look at this instrument a little bit more. If we take a look on the left-hand side here where the details are, there's a seconds between auto detections, and that's set to 10. Checking for leaks is a fairly expensive operation as far as processing of your app goes. So it's deferred to an interval, and you can change what that interval is. 10 is a nice default number. You can even force it to check automatically. There's a little countdown timer, but if you need to check immediately, you can click that button and it'll tell you. And again, here there's no leaks, so we're happy. So let's go back to here, and that's instruments. So let's talk about auto-release now. We've presented this in our memory management discussions, and it's very useful. You're able to create these functions that return objects without having to worry about what the caller does with them. You don't have to worry about the caller of your method having to release. You just send it back auto-release, and it'll get taken care of. But there are some problems that come along with that. My clicker's dead. All right. Auto-release simplifies your code. You don't have to worry about the scope. When auto-release pool pops, it releases every object in the pool. Any objects that have a retain count of 1 at that point are deallocated. And it's already handled for you in your run loop. So where's the problem here? Well, what if you have one iteration of your run loop that creates and auto-releases thousands of objects or several very large objects? You're going to have a spike in your memory use, right? So your memory use is going to go really high until the end of the run loop, and then everything's going to get released. Well, what if that memory use is so high that you run out of memory? Well, that's one of the risks you have with auto-release. So you run into what's called a crowded pool, and I'm not sure where that is. But yeah. The little dinghies aren't even flat. So we want to take a look at how do you reduce the maximum footprint of your app? How do you reduce the high watermark, the spike in your memory use? You can create and release your own pool. And we've talked about this before, where you can actually create and release your own pool inside of a loop, so that any of the objects that get auto-released inside that loop will then get released at the end when you release your pool. You don't need to do this frequently, but it may sometimes be useful, and we'll take a look at why and how. And of course, loops is the common case. So this is an example where some large number can be, let's pretend it's 10,000. We're going to step into this, and we're going to call these two functions, lowercase string and string by appending string, both of which return auto-released objects. That means by the time this loop has completed, if that number is 10,000, we're going to have 20,000 auto-release strings in our pool that are going to get deallocated the next time the run loop goes through. And of course, if we're already short on memory, that may be enough to put us over the edge. So let's take a look at how to do this inside a loop so that your auto-release pool will automatically get rid of them. If we preface the methods in that loop with the creation of an auto-release pool then the objects that get returned from these two methods, the two auto-release methods, will go into that pool rather than your run loops pool. And when you get to the end of the loop, you release the pool, and then you can go iterate back through, and your maximum usage won't go up. So what if you need some of these objects outside the scope of your pool? Well, this is an example where you have your pool up at the beginning. You call some auto-released, something that returns an auto-released function or auto-released object. You check some condition, but you need that string at the end after you're going to pop. So retain the string here. And then you release the pool. And this is similar to the early return I was talking about before. You don't break until after you've handled your memory management. And then you have the string still out here, outside the scope of your loop, to do what you wish. And another thing you can do, actually, this is what I would say is the first line of defense when you have a lot of auto-release, is don't use auto-release. If you have the option to allocate and release an object instead of auto-releasing it, do that. The memory is going to come when you need it. It's going to go when you're done with it. And if you don't need it to persist to the end of your run loop, just get rid of it. And again, in the previous example, maybe a mutable string would have done the trick. So you created one mutable string, and over your loop, you just keep changing it. So let's take a look at that. I have another example here called the high water table view. And what we see here is in view will appear, I'm going to take these out because that's not going to show the demo. But in our view will appear, we have 10,000 iterations, and we call two auto-released functions. So let's give that a run. I'm going to build that. Yes. And run this in Leaks. And then let's take a look at what that looks like for memory usage. Well, let's look at this. So Leaks you saw is when objects lose their references. Object alloc actually points to the total number of objects, and you can even go through and see what each of the allocations were. What we have here is we have a big spike. All right, so look at this. We're flattening out at about 500K. But when we first launched our application, we went up to 1.3 megabytes. So if I take a look at that, well, first of all, actually, in this view here, you'll see there's some bars on the right-hand side under the number of allocations, and then net and overall. The dark area, it's true of the dark blue and it's true of the dark red, is the number of allocations that are still around, and the rest of it, the light red here, is the total number that you've allocated over the course of your application. So let's look at CF string. We can actually step through, and there's a percentage. This is a percentage of all the allocations we've had, and as we step through, we see that 27.6% of all the allocations we've done were on NS string inside of view will appear. 20.7 were string by appending format, 6.9 were in lowercase string. So we'll go back to our code here and consider the alternatives. This is where we can actually put a pool in. And every iteration of the loop, the pool will get created, those objects will get added to that pool, the pool will get released, those objects will go away, and we're happy. So what we're trying to do now is prove that there's no spike. Oh. This computer's been giving me problems today. I may be done with simulator. Let me try that one more time. So let's try that one more time. Let's do object allocations. Yeah, this is not going to work. Well, you have to trust me in this case that what we should have seen is that the object allocation graph, instead of showing a big spike at the beginning and then flattening out when the auto release occurs, we actually just have, it goes up to our plateau and stays there for the duration of the application. So, actually one thing, let's talk about this a little more. One thing to consider in here is now what you're left with is you're allocating 10,000 auto-release pools over the course of your application, or over the course of just this one method. So another thing you might want to consider is just reducing that. The pool is useful to help get rid of these objects, but you don't need to allocate a pool for every time. So one thing you might want to consider is let's take the pool outside of this loop, and then we'll only actually release it every 100 iterations through the loop. So in this case, I'm going to say if I mod 100 equals 0, then I'm going to pool release, and then I'm going to allocate a new pool. And if we inspect this code, what we have here is we have a lot more tolerance for creating these pools because we don't need to allocate a new object every time through. And if I could use my leaks tool, my object allocation tool, I would show you that that worked, but you're going to have to trust me on this one. So let's keep going. This is actually this is exactly what I was trying to describe to you, which is that creating your objects over and over in a tight loop might not be such a great thing. The auto release, moving the auto release and only getting rid of it every 100 iterations may be a better way to go. But there's other times that you might run into this as well. Here, we're iterating over, again, let's say 10,000 times. We're creating some object, we do something with that object, and we release it. Well, instead, what we might want to do is reuse that object. So instead of creating a new one each time and setting the value, we may want to create it once outside the loop, reduce the number of memory allocations that happen, and then set the value each time through the loop, do whatever you need to do, and then the next iteration through the loop, we set the value and do it again. So again, this is up to you to decide when it's appropriate, but in this case, we allocate outside, we loop, we do whatever we need to do on that object, and then we release it at the end. Any questions on this stuff so far? Okay. And then, of course, the common case of this, which you've already seen, is in UI table view. It already tries to do this with cells, where you allocate the first thing you do when it asks you for a cell is you ask the table view to dequeue a cell for you. If there's one available, then you just use it. And if there's not one available, then you can go and allocate one. But here's a example where that's well used. And the last thing I want to consider with memory is memory warnings. So the system can give you some hints to tell you when your OS is running out of memory. And it'll give you these warnings that say, well, it'll give you a warning that says, we'll show you in a sec, did receive memory warning or something like that. But the thing you need to know is that you're not running alone, right? Your app is not the only thing running on the OS. The user might be listening to music, in which case the iPod app is running. Mail might be running in the background. And if mail's running in the background, it may be fetching mail from the network. All of these things are competing with you for memory at the same time. When the system is running out of memory, it's going to tell you. It's going to say, it did receive a memory warning, and it gives you an opportunity to go and clean up. It gives everybody the opportunity to clean up. It actually calls these guys and says, did receive memory warning as well. And they dump whatever memory they can. If you're successful at dumping the memory, you can keep going. Everybody can keep going. And maybe at some point in the future, you'll have this problem again, and it'll tell you. And if you keep cleaning up, great. If you're not able to dump the memory you need to run smoothly, it's going to start killing off what it can to help your application along. And the first thing it does is it kills the background applications. So your user may experience the iPod app just stop. And then if that's still not enough to get you the memory you need to run, then you're gone too. So memory warnings. Every view controller gets a did receive memory warning. Whether or not that view controller is visible, as long as it's been allocated and registered. By default, it releases any views that it's displaying that it's holding onto if that view controller is not displaying on screen at the moment. And then it's up to you to dump whatever other memory you don't need at the same time. So here's an example of a call. This gets called, this is on your view controller. You always want to call super. Make sure that it dumps the view if it doesn't need it. And then if you're holding on to something, let's say, a 1 megabyte image, you dump it here, and then you nil it out. And if you remember from the getter that I showed you before in the lazy loading, because we nil it out here, then the getter is going to note it. Next time you call that resource, it's going to notice it's not there, and it's going to try and load it again. And you only have it when you need it. And then there's another warning you get, which is it's actually the same warning, but at the app delegate level. So if there's anything you want to catch that's not involved in a view controller, let's say you've got some cache of images outside of your view controller, you can catch that in your app delegate call. So what do you want to dump? Well, I mean, the short answer is anything that you can get back. So if there's images that are stored in resources, if there are sounds, something you're fetching from the web, data from the web, images from the web, that's the best stuff to dump. And if you get rid of it all, you can go fetch it again when you need it, and you should be happy again. You can actually, in the simulator too, if you take a look at instruments and you're running and you look at your object allocations, you look at your memory usage, there's something in the simulator called Simulate Memory Warning. And when you hit this, it'll actually send out all these notifications, and you can inspect and see what actually happens in your app, how your app reacts to these things. If your app is well written, what you'll see in instruments is you'll see your application's memory usage climb, and then you simulate a memory warning, and you should see it drop right back down.
It's a good way to verify behavior, but it's not a substitute for.
So Evan says it's a good way to verify behavior, but not a substitute for developing on device. So. And then, of course, another memory technique, which we talked about last week, is using SQLite as your data store. SQLite is obviously very efficient. It's fast. It's meant to be used on these small memory situations. So consider using that as your data storage. And if you want to find out more on memory performance, you can click on this link in the slides that we post. So now the next thing I want to talk about is concurrency. Well, what is concurrency? Concurrency is multiple chunks of code running at the same time. And why is it important? Well, if you remember from the Presence 2 demo that we did last week, when we launched the application, the first thing we did is we hit the network and said, go and fetch me all of the data for these Twitter accounts. And if you remember from the demo, that was a black screen for about, I don't know, on this Wi-Fi connection, it was about 10, 15 seconds before it actually came back and gave us all the data we needed. So how would concurrency help us? Well, for that app, the user sees it as a black screen. It's hung. They can't interact with it. If you were able to do that fetching in the background, then you could put up a loading screen. The user can still interact with it and hit buttons, and you're not held up waiting for that network resource to come back. So, again, it comes down to user interaction. So you want to separate your code so that it can run certain parts alongside each other, so that one is not blocking the other. And there's some there's some things that make this difficult, but if they're well designed, you'd be pretty useful. So threads on the phone, again, this is all Unix based under the hood, right? So these are POSIX threads or pthreads. If you want to create your own threads using pthread headers, that header is there. Same header that you have in Unix systems, pthread.h. But there are higher level wrappers in Foundation that make this even easier. There's something called NSThread. And NSThread creates a run loop automatically. It's Cocoa friendly. So it knows that you're going to want to do a lot of things in this run loop, create timers, listen to events, listen to notifications. So a run loop is created for you automatically. Every NSThread needs its own auto-release pool, and that's up to you to create inside of your thread method. And there are convenience methods for sending messages back and forth between different threads, particularly to the main thread, which becomes pretty useful in the case that we're going to get into here, which is I have some, let's say this is a button hit, and I need to go do something that's expensive, right? So when I hit that button, instead of actually doing the work inside of this action, I launch a thread that goes and does it. And it's just as simple as, it's a target and selector that you send with an object as a parameter. So we're going to launch a new thread. The selector we're going to launch to is self, and it's going to be do work, and we're going to send in some data. The do work method that we've implemented on self has its own auto-release pool. It does something that's fairly expensive for the system. And then when it's done, it tells the main thread it's all done. And it sends in the result. And there's even an optional parameter here that says wait until done. So should this thread hold itself up, waiting to know that the main thread has completed listening to this message? Generally, this is no. I don't know if I've yet to run into a case where this is yes, though I'm sure you can conceive of one. But generally, you want to write stuff so that it doesn't have to block. And yeah, of course, you release your pool at the end. And at this point, when this method is done, your thread is gone. It just goes away. It's finished. So UIKit and threads. Well, UIKit is not thread safe. So a lot of the things let's say you're interacting with visual elements on the screen. You have an image view. You can't set that image view's image from different threads. You want to do all of that stuff from the main thread, which is why it's important here to message the main thread to tell it that it's done, so that the main thread can then go back and tell the views on the screen to update themselves appropriately. But the point here is that you should not be changing your views from anything other than the main thread. One little extra point here actually is that you can create a UI image on the background thread. You can load it. You can convert it from data. But you cannot set it on an image view. So let's look at, I don't know if this is going to work, threads and Xcode. Let's look at the code. Let's give it a try.
Try quitting Xcode too.
Yeah, that's a good idea. So let's make a thread. All right. Well, this is fairly simple code. Yeah. Okay. Okay. Oh, I see. There we go. First, let me give this a try and see if it's going to actually work. Okay, it actually runs. First, let's inspect this app. Let's take a look at the nib first. So the nib has a few components here. We have a button. We have a label up at the top that asks the question, what is the meaning of life? We have a button that when you click it is going to go and compute, figure out what the meaning of life is. We have a spinner here, and we have another text label. This question mark is actually a text label that's going to tell us what the answer is. So let's look at the code now. If I go through our app delegate, again, we have 4 instance variables here. We have window, spinner, answer label, and button. When we're done launching, we clear out that answer label. And there's an action that's attached to that start button, and it's begin deep thought. So the first thing it does is it starts animating, and it hides the button, right? The button, while you're calculating what the meaning of life is, you don't want somebody to interrupt you, so you hide the button. And here we're going to actually detach a new thread. So we're going to, in the background, go ahead and figure it out. And on this thread, because we're good citizens, we first create a pool, an auto-release pool. And then this is just for demo's sake, we're just going to sleep. We already know the answer, so we don't have to compute it. We're going to sleep for a little while, and then to show that we're actually not blocking the main thread. And when we're done, we're going to tell the main thread that we're done, and it's going to send back the answer. And then when the main thread gets that message, it'll stop the spinner and set the answer to on the screen. So let's run it. Here we go. What is the meaning of life? My button went away. There's my spinner. And 5 seconds later, the answer is 42. For those Douglas Adams fans in the crowd. OK, so what would happen if we didn't launch that thread? I want to show you this really briefly, really quick, which is what if we didn't separate a thread here? We didn't launch a new thread. We actually just called background thinking. Self background thinking. Well, keep in mind, this is actually going to block the main thread, which means any drawing is not going to be able to occur. So I'm going to click the start button. If you remember when I clicked it before, the start button went away. We saw this nice little spinner that was animating. So when I click start, we're waiting here, calculating for 5 seconds, and then the number comes back. Again, this is presence 2, right? This is when you're off to hit the network, you're stuck, you're waiting, right? The threads give you a way to avoid that. So that's threads in Xcode. Locks, an important piece. Anybody who's taken CS theory classes should know about locks. But the Cocoa gives you some good constructs to deal with these. Locks make sure that different sections of that a section of code doesn't get entered twice, or that different sections of code that would conflict with each other don't get entered at the same time. So Cocoa provides the NS lock and the NS condition lock and other subclasses. And the way you use them, I love this clicker. Is, well, you actually have to allocate a lock. Let's say you did that in your init method. When you have some block of code you don't want anybody to enter twice, you just say lock. When you're done with that block of code, you say unlock. And what happens, let's say you've got 2 threads that are each trying to call some method. The first thread is going to get there first. It's going to lock. There's nobody else that has that lock yet, so it's going to take the lock, and it's going to keep going. A second thread comes in, and it says some method, and it goes to take the lock, but thread 1 already has the lock. So thread 2 is going to sit there. It's going to wait. And then when thread 1 is done, it unlocks, and then thread 2 can then enter that chunk of code and then do what it needs to do and keep going. Yeah.
If we could go back to the last slide. Yeah. So one thing I wanted to point out is, remember last lecture we were talking about how if you send a message to nil, it'll just kind of silently do nothing. One really, really common mistake to make with locks in Cocoa programming is if you forgot to initialize your mylock right here. So let's say mylock is an instance variable and it's nil. Calling lock and unlock here is just going to do nothing. So you might think that you're actually protecting your code, but meanwhile, memory is getting smashed and things are stomping over one another. So just something to keep in mind as far as multi-threaded programming and Cocoa goes.
So another variant on lock is a NS condition, which is useful if you're trying to write something that creates objects or creates data and have another function that consumes that data. And the way we do it here is similar syntax. We have this condition that we lock, and then we set this Boolean to yes, to say, so we go and we calculated a bunch of stuff, and then we say new data exists set to yes, and then we do something called signaling. And the signaling goes, and it wakes up another thread that's waiting, and then it unlocks. And so here's our consumer thread. So it comes into here, it wants data, so it locks, it waits until that Boolean is set to true by sitting on this wait. And wait is actually equivalent to sleeping, right? So it actually, it just sits there until it gets a signal message on that same lock. When it gets that signal message, that thing goes and wakes up, checks to see what the value is. In this case, it's set to yes. It does whatever it needs to do with that data, sets that back to no, and unlocks because that chunk of code is done. Yes?
So if I wait forever.
Right. So the question is, if you forget the signal, what happens? Well, the whole point of this NS condition is that the signal is what wakes up this guy. And so if you're sitting here waiting and this guy doesn't signal, that's not going to go anywhere. There's another variant of this, which is broadcast. So signal, let's say you've got 5 different threads that are each waiting on that condition. Signal actually goes and tells, I believe, just one of them to wake up, whereas broadcast would go and say to all of them to wake up. So that's the difference between the two. Danger of locks. Again, Evan pointed a good one out. Yes? That's a good question. So the question is, I have two threads here, both of which have these blocks that start with lock and end with unlock, right? Lock and unlock. If this guy takes the lock and then falls into here, how is this guy ever going to get past that lock? Well, the answer is that wait is actually equivalent to unlock, sleep, and then a lock. So if this guy enters before this guy does, he's not going to get any further than lock. He's going to be stuck there. But if the opposite happens, if thread 2 gets there before he gets into his lock, he's going to check to see if the Boolean is true. It's not, so he's going to wait. Then at some time in the future, he's going to come in, thread 1's going to come in and lock. He's going to set that to yes and then signal, and then wake it up. So it's a little weird, but it's actually, when you get your head around it, it kind of makes sense. But this lock is the same as the lock you saw previously. It's just that this is a safeguard or a way to wait for data, right?
Maybe one takeaway here is that multi-threaded programming is really, really complicated and hard to get right. And we're actually going to show you a much easier way to handle multi-threading a little bit later in the lecture. But yeah, we can talk some more about NX condition offline, but it's probably going to turn into kind of a rat hole.
Well, one little tidbit here is, so I'm building remote. The last few days of, my 1.0 release, I spent like 3 days just trying to figure out all these locks. And I had things that were off fetching on this thread and things that were consuming on this thread. And I just had, and in the end, it was like one line of code that was just, I don't even remember. But these locks, they're incredibly hard to debug. There's things that are waiting for each other. One of the things that makes them hard to debug is that there's these timing dependencies. And when you have these timing dependencies and you introduce something like a debugger, that actually changes the characteristics of what's happening and makes it impossible to debug sometimes. So yeah, locks are a pain in the butt. And there are better ways to do it. So again, there are lots of problems. Deadlocks you're probably familiar with for those that have taken CS classes, which is you have one thread that needs resource A and wants resource B. You have another thread one thread that has resource A and wants resource B, and another thread that has resource B and wants resource A. The two of them are just stuck in this deadlock and they're never going to proceed. And then priority inversion, you can run into a case where the least important parts of your application have this lock for long periods of time, blocking the most important pieces. So we try to avoid locks when possible. This is the debugging problem I was trying to describe. Code may be more difficult to maintain. Let's say you have all this like subtle but functional locking code, and somebody wants to come in and make a change to how things work, and they don't quite have their head around it. It's a very hard thing to pick up. And in some cases, lots of threads doesn't mean that you're going to run a lot faster, right? Sometimes lots of threads means you're going to run a little bit slower, right? I mean, the very basic case of this is, if you have a couple thousand threads all running at the same time, they're each getting a slice of time from the processor, but every time the processor switches contexts, it needs to load and unload registers, it needs to change its own context. So there's downfalls of that. You want to give your Aperture example? This is a particularly interesting case of threads hitting the system pretty bad.
One example that comes to mind here is, especially when you're depending on a resource that doesn't scale to many threads. So there was a time when I was working on a product at Apple where if you tried to import a bunch of images from a DVD, it would spawn off maybe 10 threads, each trying to pull in images from this DVD. So these threads are getting context switched in and out, and each thread gets a little bit of time, and it says to the DVD drive, all right, spin to this place on the drive and start loading this image. As you know, optical media is much, is pretty slow. So it took something like 10 hours to import, these images from a DVD, where really, more threads here did not mean that it was faster. It probably would have been more optimal here to just have one thread dealing with the DVD.
So there's other ways to approach this, and the best one, well, actually, before we get into NS operation, which is pretty useful, there are some constructs already available to you in Foundation and UI kit that will abstract the threading from you, right? So you don't have to deal with launching a thread, waiting for the response and signaling. If you look at NSURL connection allows you to hit a website, send a URL, and wait for data back by setting a target and a selector, target and an action, which you should be familiar with from interface builder programming. So basically, you say your NSURL connection, you set the URL that you want it to fetch from, and then you tell it to call this object back with this method, and all the threading's under the hood. So that's one case where this could be a lot easier. Timers are also very useful. So you can create a timer, tell it to fire off in 10 seconds, and it'll call you back on the run loop, on the thread that you actually initialize that timer on. I use timers a lot. And then operations. This is kind of a higher level way of looking at why you're threading and thinking about operations as units, the calculations that you're trying to do as a single unit. So let's look at NS operation. It's an abstract superclass. It's nothing on its own. It manages creation and lifecycle of a thread. Right? It encapsulates a unit of work. So basically, an NS operation, you set up a main function and you do all your work in there. And you deal with this as a single object that you can pass around. And that object, you can specify its priority and its dependency on other operation objects. So if you have a tree of operations that need to occur, you can say that this guy, which calculates this set of data, can't happen until this operation is complete, which goes and fetches some set of data. And here's another operation that fetches something else, and that's even more important. And there's something called a queue that will organize all that for you. So creating an operation subclass. Well, you create your init method, and since your operation probably needs a context, you create an init method that takes some object, and you set that locally. And then you implement your method in main. So your NS operation subclass implements a main method that goes and does the heavy duty lifting, the work, right? Then you add these things to, well, let me skip ahead a slide and talk about that. We add these things to an NS operation queue, okay? And the NS operation queue allows you to add all of these different operations, set the priorities and dependencies on the operations, and it will schedule them appropriately. So it'll make sure that the dependencies are respected, the priorities are respected when it can. And you can even tell it that you only want one to run at a time. You can let 5 or 10 of them run at a time. So let's go back. NS operation, again, is, when you want to use NS operation, you generally have to subclass it, and you have to implement, class, your own custom class for that. If you want a really light way to do this, take a look at NS invocation operation, which uses the same target and selector that you've seen elsewhere in Cocoa, where you create an NS invocation operation, you tell it what method you want it to call, what object to take, and what object you're calling it on, and then you can add that to the queue instead. So this is just a lightweight way of dealing with NS operations. This is actually a subclass of NS operation itself. So let me do a little demo here, which again, we'll look at our Flickr app from last week. And we've changed this around to deal with NS operations rather than having to do everything on the main thread. So here we go. Let me give us a little more space here. All right, well, there's a couple of things here. First, when we initialize our table view controller, right? If you remember, let me run it really quick so we see what it looks like. This is loading. It goes and it fetches all of these Stanford tree images, and it fetches the images for them. Well, the first thing we did was the actual going and fetching the list is one operation, and each of the individual fetches of the images are individual operations themselves. So let's take a look at how we did that. In my table view controller, we create the operation queue, and we say that we just want one to happen at a time, so a single operation at a time. As we go further down here, in view will appear. So the first time we're going to display the table, we show this loading indicator, which is the spinner you saw. But we do this begin loading Flickr data, and if I move down to see that, that actually allocates an NS invocation operation, and it does so with the selector for synchronous load Flickr data. And then it adds it to the operation queue, and then it releases it. So let's look at that again. Synchronous load Flickr data, there's no object that needs to get passed in. And synchronous load Flickr data creates a URL, and then it says string with contents of URL, which goes and hits the internet. And then when the data comes back, it parses it as a JSON string, JSON data, and then it tells the main thread that it's done. Okay, so let's look at what that does, which is loop through each of the items that got returned and then reloads the table. So one thing to note here is this operation, there's a lot of things that we didn't have to do. We didn't have to launch a thread. We didn't have to create our own auto-release pools. Really all we did was we told the NS operation that it should look at this and that it should schedule it. Now, that gets us the list of images. Well, how did we do the individual images themselves? Well, let's look at cell for row at index path. Okay. So this is when the table view actually wants to display a cell in the table. So, well, why did we do it here? We could have, when we got back the list of images from Flickr, we could have gone at that moment and said, well, I want every image in that list, so go and just fetch it for me. Well, instead of doing that, instead of fetching, that list could have been several hundred images. Instead of going and fetching every one of the 100 images, let's wait until the table tells us it actually wants it. We'll go hit the internet, get the data, and then load it back. Yeah, lazy loading again. So here we are, cell for row at index path. Again, here's our reuse of objects for the cell. We dequeue it if we don't have one. If we do have one, if we don't have one, we allocate. And then here we say cell.image equals cached image for URL. Let's look at that. So cached image for URL goes in and says, first it checks to see if our cached images array or dictionary has the object that we need. If it doesn't, then it goes and it creates its own operation. And again, this is actually its own subclass, image loading operation. It allocates it with the URL that we want and the selector that we want it to call when it's done. It adds that to the queue. Oh, this mouse. Adds it to the queue and then releases it. So let's look at that class. Well, this thing, there's our init method, which store off what gets passed in. And then in the main, right, this is how the operation knows when it should start actually executing. In main, it hits the web. It says init with contents of URL, gets the data back. The data gets turned into a UI image, and then the result gets turned into a dictionary that gets sent back to the main thread. And on the main thread, we call did finish loading image, which is here. And we take out the image from our and put them into our cached images dictionary. One sec, and then we reload the table, and we're done. Yeah. Right. So the question is, let's look at this again. Init with contents of URL. Yes. The question is this a blocking call? And the answer is yes, right? So this is not going to return until it's hit the internet and the internet has said, until Flickr has said, okay, here's your data. So this may take a second, this may take 10 seconds, it may take less. But the point is that this operation is running in its own thread that was created for you, not blocking anything.
And NS operation queue manages creating and destroying those threads.
And NS operation queue, automatically creates and destroys those threads for you. So, yeah, that's NS operations. Super useful. Actually, this is new to Leopard. I actually hadn't known about it till pretty recently. And the more I've been diving into this, the more excited I am about all the code I can dump in my apps that I've created to do this stuff. I mean, this is super fun. So, any questions about this stuff before I move on? Okay. The last thing I want to get into, just with the last 10 minutes we have here, is, if you want to learn more about Concurrent, click on this link. The last thing I want to talk about are just some general tips and tricks. We've talked about two major things with regards to performance: memory management and concurrency. But there's a lot of little things that you should know about in your application if you want to, be a good memory citizen on the phone. One is drawing performance, and we've talked about a lot of this. But one thing that's very expensive on the phone is compositing different layers. So let's say you have 2 layers, and the top one is transparent, and the bottom one is not. Well, the UI kit has to actually Core Graphics has to go and composite those 2 images together. But let's say that the background image that we're talking about here is just a white background, and the guy on top is just a white background anyway. It's just transparent. We know the background is going to be white. You can make that view opaque, and by making it opaque, it's going to actually draw a lot faster. There's tools that'll help you with this. There's actually a core animation instrument that you can run when you're profiling on the device that will show you where your overlapping views are, where your transparency is. And if you can reduce those down, you'll notice your table view scrolling, for example, will just get so much faster. If you have these transparent labels on top of white backgrounds, you're going to scroll. You'll scroll on the device and you'll think, oh, that feels pretty good. And then you'll go into this instrument, discover your transparent, turn that into opaque, and just watch how smooth. It's like butter. It's really cool. Another thing to note here is you never call draw rect. You actually want to call set needs display, and then the view tree will manage actually calling draw rect when it's appropriate for you. So that's a good little performance tip. And then another one here is if you know what the rect is that you're invalidating when you do something on screen, instead of calling set needs display on the entire view, call set needs display on just the rect that's changed. If this is a UI image view, for example, where it's trying to display an image, that might be expensive for it to actually go and re-render that image. If it can just do a small square portion of it, it might actually be a lot faster. So reuse table views. I don't think there's really much I need to say here, except that UI table view already has this way of dequeuing reusable. This is the whole reuse model of objects. Yeah. Yeah, so the question is there a way to reuse the cell if the row height is changing? Row height is actually another data source method, I believe. It's either delegate or delegate method. So when the table gets reloaded, it goes and asks you for all of the new table cell heights. And then, yeah, you don't need to worry about that. So the reuse works with that. Get notified. So don't poll, right? You know what polling is? You're basically asking some resource, are you ready? Are you ready? Are you ready? Are you ready? It's annoying, first of all. Second of all, it's a lot of wasted time, right? We'll talk, I think, next week about notifications. And you've probably seen these in the headers already, but notifications will tell you when something changes. When something significant happens, you can be told when that happens. You've also seen this with the whole target and action paradigm to get called when something happens, as opposed to asking all the time.
Device rotation is a great example from UI device data.
device rotation. So Evan says device rotation is a good example of this. You don't want to always ask the accelerometer, are you vertical, are you horizontal, and then do the right thing. You want to wait till the system tells you that that's changed. And then the last thing here is to take samples. Another one of these instruments that are really handy is the CPU sampler. And CPU sampler will actually periodically, I think 10 microseconds is the default, or 100 microseconds, or some number is the default. It goes and it takes a backtrace of your application, and then it builds a graph of where you're spending most of your time. And the reason that sampling is important is that you don't want to go and just blindly start optimizing your application, right? You want your application to run fast, great. And you should want all of your application to run fast, great. But when it comes down to shipping something, you don't want to be optimizing some small part off over here when there's a big piece of your app loading or your view display or something that takes a lot of time. What you do is you run the CPU sampler instrument. It'll tell you where your application is spending time, and then you know where to invest. Then you know where to invest your optimization cycles. So yeah, use that. And then just a quick little recap here, which is that performance is not, it's an art, right? You need to figure out what's right for you, what's right for your circumstances, and make the appropriate choices based on that. Don't waste memory. Don't ever waste memory. If you don't need it, don't use it. If you could dump it, dump it. Concurrency is a little tricky, but there's tons of little, the NS operation is a nice little construct for doing those well. And of course, drawing is fairly expensive, so don't do what you don't need to. So that's it. That's performance. Any questions? Final questions on this? Okay. Oh yeah. Let me give you a little demo of next week's assignment. So I'm not going to show you code. Obviously, we. Where did that go? Oh, no. 1 second.
We can show it on Wednesday.
Oh, I have it. It's down here. Hopefully this just works. Let's quit that simulator. All right, well, here's what next week's presence assignment is going to look like. Fairly similar to what we've seen in the past. As we click through on each of these, we can see what William Shatner's saying, what MC Hammer's saying. This mouse is a pain in the butt. The difference here is that if you notice when we loaded, let's load it again. Well, you saw the loading screen for a split second there while it actually went and fetched the data. That's the big piece. That's one of the two big pieces for this assignment. So is that we're going to make this concurrent. Another big piece, which you're going to learn about on Wednesday, is this. How do you do these overlays and how do you handle text input? So in this, we're actually going to be able to, tweet. This is actually Evan's Twitter account. So what am I going to say? I am hungry and need a burrito. So if anybody's on Evan's Twitter, you just got a message. Anyway, that's what we're going to get to for next Wednesday. That's it. Thank you very much.
For more, please visit us at stanford.edu.